Good morning, everyone. We'll come to lecture 6. Lecture 6. So today we'll talk about spin orbit coupling. So we'll talk about two cases of spin orbit coupling today, and the lecture probably won't be very long today. Just two cases. Okay, so the spin orbit coupling has a Hamiltonian. Spin orbit coupling Hamiltonian. So this Hamiltonian is derived from the direct equation. So this is a Hamiltonian of an electron moving in an electric field. We derive this. So there are two contributions to this Hamiltonian. One is the when the electron moves, there's an effective B field due to the relative motion, and then there's the Thomas precession. Two parts. But anyway, that is the form. Okay, so you can use it directly. It is a general form of a spin orbit coupling. And here, this electric field is a general electric field. Any electric field you plug in there, then that will give you the contribution. And from there, from here, you can already see that as long as the electric field and the momentum, they are not pointing at the same direction, you will make this term finite. So spin orbit coupling happens very generally. As long as your motion and the electric field are not pointing in the same direction, this term will give you the energy. And that is the spin orbit coupling. It's very general, okay? So today we'll consider two cases. So in condensed matter, the electric field usually have a certain form in our theory. You cannot just use a chaotic electric field. It's difficult to do it theoretically. So today we'll consider two kinds of electric field and the corresponding spin orbit coupling. So the first kind is called the rush bar. The rush bar spin orbit coupling. They are in 2D interface or 2D materials. So what is a rush bar spin orbit coupling? Rush bar spin orbit coupling is just this Hamiltonian in a particular form of the electric field. Okay, so let's consider 2D system with a perpendicular electric field. Electric field. We'll make electric field equal to this form. So basically, the system is this. You have a plane. This can be a 2D plane, or it can be a 2D interface between two bulk material. Like you have one bulk material, another bulk, and then they have an interface. For example, you can have a 2D material, or you can have a bulk material, and then the bulk material has an interface. Let me use a different color. Okay, you have an interface. Let's draw it like that then. So here you have an interface. You have one material on top, the other material in the bottom. So the key thing here is the symmetry, is that there's an electric field in the interface. As long as your two materials are not exactly the same, you will have generally you will have a vertical electric field, because the system has no symmetry, no mirror symmetry. So one material on top, a different material in the bottom, then in the interface, there's generally a little bit charge transfer, and then you have a vertical electric field. If you have a 2D material, then you use a dual gate, then you can apply an electric field. You can also apply electric field. So rush bar spin-optical coupling happens when the electrons are moving in a 2D plane, and it experiences a vertical electric field. Then that will give you a certain energy due to spin-orbit coupling, and that is the rush bar spin-orbit coupling. Is that okay? The electric field is quite simple. It's just vertical, quite simple. And then you have an electron. Okay, you have an electron moving. Okay, with a P. Okay, moving with a P. And here the same. You have an electron moving with a P. Okay, then let's see how this will change the Hamiltonian. Okay, so this is the Hamiltonian, and then let's change this Hamiltonian a little bit into a form that is easier to deal with in this case. So you look at this part. So the I component is this, not I component. This is a dot product. So basically, you sum over I. So I'm using the Einstein summation convention. When you see two indices repeating, that means you automatically sum them over x, y, and z. So E cross P, I component will be I, EJ, P, PK. IJK, EK. Okay. Then we want to move the electric field out. So we move the EJ out, and we add the negative sign here. And then at the same time, you change J and I. You change. You add the negative sign here, and then you change J and I. Change the J and I order. Okay. And then you move the sigma I inside, and then the K inside. Then here, you can see that this is sigma cross P J component, and then you have negative EJ, negative E dot sigma cross P. Okay. So in this way, we move the electron out. And then you can add it here. This negative sign, cancel each other. So you have EH bar 4m square c square sigma cross P dot Z. Okay. Then you can just use a parameter. So you just you just group this whole thing as alpha. So this is a parameter that depends on this, but in a solid state system, it's not a free electron. The effective mass is different. Okay, so generally this will be a material property. Okay, so in solid, alpha depends on the material and interface property. For example, if the electron is in the solid, then usually you use the effective mass, not the free mass. So you need to like modify this according to the solid. But overall, this is just a constant that depends on material and interface property. So the key part is this part. This part will give you the form of the energy dispersion. Is that okay? Any questions? Okay, so let's consider the Rushbar coupling term. Spin orbit. The spin orbit coupling. The Hamiltonian will be R. R means Rushbar. Okay, so now this is just a Z component. It's just the Z component because you dot Z. So you take the Z component. So when you take the Z component, then it's just X sigma X Py minus sigma Y Px. Okay, Px. And then when you write it out, it will be of this form. It will be, I mean, sigma X is 1, 1, right? Py minus sigma Y is negative I Px. And Py is just okay, so you just write it together. Py plus Px. And Py minus Px. Okay. Okay. So we need to diagonalize it. This matrix is pretty simple. Okay. You diagonalizing the H bar will give you a dispersion like this. And then the E, you use Rushbar, then Rushbar energy will be plus and minus this. This one will be alpha and Px Py squared. You solve it, then it will be plus and minus P. Okay. So if you plot it out, it will be a cone. If you plot it out, then you get a cone. Not showing very well. Okay, something like that.
Why is left number?
Yeah, you can change it. Doesn't matter. Okay. Okay, you can change this. Probably it doesn't matter too much if you just consider the energy. Because it's isotropic anyway. Okay, so you get a cone like the direct cone. But this cone is produced by spin-orbit coupling, not like in graphene. In graphene, is you get a cone, but the underlying reason is not spin-orbit coupling. For rush bar, will give you a direct cone. I mean, I should not call it a direct cone because it's not from the Dirac equation directly. It's just from one term of the Dirac equation, the spin-orbit coupling term. Okay. So I should not call it a direct cone, but it's a cone. Okay. Of course, this is somewhat like similar to the Dirac equation, but not exactly. You can already tell the difference because in the Dirac equation in graphene, this is sigma x px, sigma y py. If you recall the Hamiltonian of the graphene, this is sigma x, sigma y, pu, sigma x px, sigma y py. But here it is sigma x py and sigma y px. This is a cross. In graphene, that is a dot. Okay, so it's different, but they produce the same energy dispersion. But later you see that the spin texture will be different because of this cross term. Okay. So and this slope here, in graphene, this is determined by this Fermi velocity, but here is determined by this rush bar coupling parameter. Okay. And you can see that this is related to the effective mass, related to the effective mass square. Okay, if your effective mass is small, then this alpha is going to be big, and the slope of the cone will be bigger. Okay, so the math is not complicated. Okay, the interesting thing is the spin texture. This cone has a very interesting spin texture. Okay, so so let's solve the wave function. Okay, let's py plus ipx equal to p e I theta. So here we are going to use the py on this axis, and then the px in this axis, and then and then this is the angle, and then this is the angle. Okay, so the Hamiltonian will be alpha p, and then it will you just use the polar coordinate. So you change this Hamiltonian. You change this Hamiltonian into this. I should use plus and minus. Plus and minus. Okay. Okay, so let's calculate the eigenstate. The eigenstate is okay. So you can just calculate it. Let's say you have an eigenstate equal to E equal to plus and minus P. Okay. Then we just solve it then. Okay. You solve it then copy equal to Copy. So from here, you can already delete this parameter here. So let me decompose into make it into a two-component wave function. Okay, so you can already cancel this out. So you have this EI equal to plus and minus this, and then equal to plus and minus this. Okay. So I think you only need one of the equation. You can get the solution. Okay. So basically you have plus and minus 1 over this equal to this. And another important thing is this need to equal to 1, the normalization condition. So for example, okay, so let's set if this equal to 1, then this will be just be let me see. Then I mean, if this is 1, then okay, then you have this. So the answer will be 1. Then will be plus and minus this with the normalization constant. With the normalization constant, this will be 1. This is 1. So the normalization constant will be this. I think there's another way you make it more transparent. That is, you use this. So you multiply half of the phase, then you get this one. Okay, this is negative. I mean, you can always multiply a phase, right? Or I should not say equal. Okay, or because it's a phase, they're not exactly the same. Okay, but for a wave function, you can always multiply a phase. Okay, so this is the wave function, and you need to know that this is a spinner. So this is the state of the spin. So different state of the spin will give you a different energy. So let's look at the top view. So on the top view, I mean, this is the cone, right? This is the cone. So you look from the top. Then you will see. You will see. I'll draw it in this way. this. Let me see, x, y. So let's draw in a normal coordinate. Okay, just normal orientation of the chord. Let me make it longer. Okay, px, py, and then let's draw a circle. Okay, put it here. Okay, so this is the circle. Okay, so if you look it from the top, you see a cone that is a circle. So let's look at the spin direction. Px. So let's look at let me see. This one. Copy. Okay, if theta is 0, we need to go back to the definition. Let me copy this definition. So if theta is 0, it will be in y. Okay. If theta is 0, you're going along the y direction. Okay. So if theta is 0, then the wave function will be what? 0. This one will be plus and 0. This will be 1. This will be plus and minus 1, and then this will be 1. Okay, so if you remember, let's look at the top one, 1, 1, and negative 1, 1. So this is the eigenstate of sigma x. Okay, the eigenstate of sigma x. So when you solve the spin have 3 kind of eigenstates, right? So the Asx plus and minus the eigenstate. The eigenstate will give you plus and minus 1. Do you know what I mean? Like, because Sx is proportional to this. Okay, Sx is proportional to sigma x, and sigma x is this matrix. If you solve this matrix, then the eigenstate, the eigenstate of sigma x will give you this eigenfunction, eigenstate. Is that okay? If you solve sy, this is proportional to sigma y, you will have I think negative I, and then the y direction will give you, I think, plus and minus I1. Okay, if you go to z, then the eigenfunction of this will give you 1 or 0, 1. So these are the eigenstate of the spin. Okay, if you apply magnetic field in the x direction, then the 2 eigenstates will be this. Okay, so this will be the spin pointing in the x direction. Plus and minus is this direction or the opposite direction. If you apply If you apply magnetic field in the y direction, then the eigenstate will be this one. If you apply a magnetic field in the z direction, then the eigenstate will be this two. We usually deal with this two, but the other two are also eigenstate of the spin. So you say this is pointing in the positive z direction, this is pointing in the negative direction, and similarly, this is the plus and minus y direction, this is plus and minus x direction. Is it okay? If you're confused, you can go back to review how we learn the eigenstate of the spin in the quantum mechanics textbook. Usually you apply magnetic field, then you have these eigenstates come out. Okay, you look at here. What is this? This is proportional to the Sx, eigenstate, this one. So the spin is pointing in the what? In the x direction. And which direction depend on whether you are dealing with a positive energy or negative energy. Okay, so here, when you're in the y, then if you are dealing with negative energy, then it will be this direction. So this will be the direction of the spin. Is okay? Because when theta is 0, the p is py. And when p is py, theta is 0, the spin is in the direction of x direction. Is that okay? So you take the negative direction, it will be this one. Of course, you have another one pointing in the opposite direction for the opposite energy. Okay, so now, so let's look at theta equal to pi over 2. If theta equal to pi over 2, then theta will be in the px direction. Okay, so this one, pi over 2 will be what? Will be this plus and minus I. Theta is pi over 2. This will be pi over 4. Pi over 4. And this will be e negative pi over 4. And what is this? This is just I. This is just I. So this is plus and minus this is just plus and minus I. Okay. And this is negative I. Negative I. Okay. So eventually you'll get let me see, did I make a mistake? Let me see. Plus and minus.
I think you want to say theta equals pi, not 1/2.
Pi is here, right? This is pi, right? But I want it to be go along here. So this is pi over 2. Pi over 2.
Pi over 4 is not.
Okay, I see. Sorry. I mean, this still work, but let's simplify it. Let's use this part. Okay, I'm using this part. It will still work, but for simplicity, it's better to use this form. Okay, if you use this form, pi. pi okay, pi over 2. Okay. Sorry. This will be pi over 2. And then this will be plus and minus I. Okay. Is okay? And then this will be what? This will be pointing in the SY direction because this is the eigenstate of SY. Okay. So if you plot it out, it will be pointing in the Y direction. SY. This will be SY. This will be SX. Okay, so once you see this, you can put in any angle you like. You can put in any angle you like, and then you solve for this eigenstate, and then you will find that it will be the eigenstate along that perpendicular direction. So eventually, you will get a spin texture like this, and then because for each direction there will be a set of eigenstate for that particular spin, and then you will okay, so you get a spin like this. Is that okay? Is that okay? So if you go to the negative energy, then you just reverse it. Everything is reversed. Okay, so if you put it in a cone, so what does the cone look like? The cone will look like this. The cone will look something like this. And then this is just opposite. Okay, you get the idea, right? On the top part is rotating this way. On the bottom part is rotating in another way. So you can imagine. Actually, this spin texture is very beautiful. Okay, on top part, the spin is rotating like this. On the bottom part is rotating like that. Okay, so this is plus energy. This energy on the top part is plus this, and this energy is this. So you can see that this spin and this spin is flipped. That means you flip the spin, you have a jump of the gap, and that gap is proportional to the momentum. So we can understand how can this happen. So you go back to the Hamiltonian. The Hamiltonian is proportional to this thing, right? Originally, it is proportional to this. Okay. So previously, we know that you can actually understand this by using an effective electric field. So E cross P can be viewed as an effective B field. Effective B field. Because previously we already know that in like if you have a V and then on E the B field. I mean, we talked about this in the last lecture. We talked about this in the last lecture. E cross V, and this is. So yeah, basically. So this is the effective B field when the particle is traveling. If you use the Lorentzian transformation, you'll find that in the frame of the particle, it will see an effective B field due to its motion. And that effective B field is E cross P. Then you can see that this B field is in the perpendicular direction of the E and P. So that means if you have a E here, let's say you have a E field like this, and then you have a P like this. So E P, so E cross P will give you a B field like this out of plane. Okay, but if you move opposite direction, the B field will be into the plane. Okay, so the effective B field depends on your traveling direction. Okay.
First case.
E cross P.
First case, the P is pointing to the right.
Okay, my mistake. Okay, so let me use the color. Okay, I think my mistake. You have a P here. So okay, so this is actually into the plane, and then this is out of the plane. Okay. Okay, so you know that when you have a spin in a magnetic field, the direction of the magnetic field determines the eigenstate of the spin. Do you get my idea? Let's say because this sigma dot, the spin-orbit coupling is proportional to sigma dot B. This B direction determines the spin state. So here, the spin direction, this B is determines the spin. Okay. Let me see. So here, and let me draw it more carefully. So I'm trying to give you a physical picture. So the E is pointing in Z direction, and then the momentum is in the P. So this B field is into the plane. So this will be the B field. Is that okay? E cross P, right? E cross P. So this into the plane. Then this will be pointing in what? This is let's say this is X, this is Y, this is Z. Okay, so when you have a field that is in the Z direction, the momentum is in the X direction. Then the B will be, so basically here you see this is the E field, this is the P, and then this will be the B. So when you are traveling with P, your spin will pick the Y component, either plus Y or negative Y. Okay. Okay. So either way, And your spin will only have two options. You either have this one, or the I should not use negative, is the negative y spin, or the other way. Like it's two spin, spin up or spin down in the y direction. Okay. And they will give you opposite energy. They will give you opposite energy because sigma dot b. If your sigma is flipped, the energy is flipped. Like if your eigenstate is flipped. So basically, this one equal to basically b times 1/2 plus and minus, like proportional. This will give you a energy equal to this. Of course, you have the proportionality constant. So the spin up and spin down in the y direction will give you the energy. And the energy is proportional to your P. Okay, so now you can understand. Okay, so I am pointing in the x direction. The spin in the positive y and negative y, spin up and spin down in the y direction, will give me plus E and minus E. Okay, and that particular gap is proportional to the momentum. Okay, so this y you have a cone, and the gap in the cone is generated by the spin-orbit coupling. So this gap is proportional to P. Why? Because your effective magnetic field, this effective magnetic field is proportional to P. Okay, so you can understand this by using an effective Zeeman effect. You have a electron traveling in an E field. The faster you travel, the larger the effective B field will be. And the B field will always point in the perpendicular direction to the electric field and the P. Okay, so that determines the spin direction. The faster you travel, the bigger this energy gap will be. And if you rotate, you change the direction of the momentum, then the spin will rotate accordingly. And they're always perpendicular to each other. So that's why you have a cone like this. Okay, is that okay? So this is only the part in the spin, and the total Hamiltonian will look like this. The total Hamiltonian will have a kinetic energy. We'll have a kinetic energy part plus the spin-orbit coupling. Okay, so what does it mean? That means you have this. Copy. Let me make it smaller. Okay, you have this part. And this is just a parabolic function. And usually is big. How can I draw it? Let me draw it better. Draw it. Okay, you get the idea. But drawing is not very good. Okay, so you get a parabolic band. This is just the kinetic energy. Okay. Then you sum them together. You sum them together. So you see here, this is split. If you sum over it, you will get something like this. You get something like I guess something like this. Then you have this, and then you have this. I hope it's clear. Okay, let me. You have something like this. Let me shrink this a little bit. Okay. Okay, then the spin will follow this spin. This one will be this. Okay, and then the outer part will be on the opposite direction. You get the idea? Okay, so you can graphically try to sum this with this. So this is a large energy, it's kinetic energy. This spin-orbit coupling is relatively small. I mean, it depends on the alpha parameter, but it's relatively small. Why is it small? Because you have the 1/c square here. Okay, so it's a spin-orbit coupling is a small term. Okay. But here this is a normal kinetic energy. So you have a big parabolic band, with a small splitting due to spin-orbit coupling. Then you get a cone like what it's something like a I mean, what is the name of this shape? You get the idea. It's something like the Mexican head. Okay. And this is the typical dispersion for rush bar spin-orbit coupling. And the underlying reason is pretty straightforward. If you know the Hamiltonian and just draw the diagram and solve the Hamiltonian. It is not that difficult to understand mathematically. It's just a simple Hamiltonian. You solve a 2x2 matrix and examine the spin direction, and then you get something like that. Of course, if you're drawing a larger energy scale, you will see something. You will see something. Probably if you're in a larger energy scale, if you're in a large, I think a large energy scale, but probably a more realistic. A more realistic will be a small splitting. Will be a small splitting, because this spin-orbit splitting is small. So if you're really drawing in a very large scale, then you have two dispersion, like they have opposite spin. Okay, so the picture is pretty, I would say, pretty beautiful. And this small gap here, this small gap is the energy gap due to spin orbit coupling. So first, you need to know that P is still a good quantum number. P is still a good quantum number. Why? Because the spin-orbit coupling does not break the translation symmetry of the system. So you still have a momentum. So all of these states, they are still a good quantum state for P. But due to the spin orientation, then there will be a splitting. Okay, there will be a splitting. So this is one example of the spin-orbit coupling. So let me give you one more example that is not exactly spin-orbit coupling, but the graphene. Okay. For graphene, we know that it is sigma dot P, right? If you solve a graphene, you have sigma dot P. Proportional, okay, proportional to sigma dot P. So if you solve graphene, I can leave this as a homework for you. If you solve it, this will be proportional to Px plus and minus IPy. Px is negative I. Negative. Okay, you can try to solve this Hamiltonian and follow exactly the same procedure that we have done here. Okay. Actually, we already solved it before. We get the eigenfunction. So if you plot it out for graphene, graphene has a cone like this. So the cone of graphene will be something like this. And here, because it's a dot, so sigma x is related to px. Okay, sigma x is related to px. So your spin is still in the x direction. If you travel at x direction, okay, if you travel in x direction, then you're dealing with sigma x. Okay, previously is sigma cross p. If you travel in the p direction, you're dealing with sigma y. They're perpendicular. But now, if you travel at p, you're dealing with sigma x along the p direction. So the spin will be spin up and down in that p direction. Okay, so your spin will be this. Your spin will be this. The spin will align with p direction plus or minus p direction. So if you draw the spin, it will be something like this. Okay, and then here will be inward. Okay, but for graphene, it's not due to spin-orbit coupling. For graphene, this is just directly just the kinetic energy. So you don't have this for graphene. You won't see something like this. You won't see something like this. Yeah, sorry, I didn't draw it well. Okay, you will not see something like this. I don't think you have ever see anything like this in the literature. Maybe I'm wrong, but at least I'm not aware of it. I've never seen I've never seen something like that. Okay, why? Because this is already due to the kinetic energy. This is not due to spin-orbit coupling. Spin-orbit coupling is what? Is cross. You just remember, spin-orbit coupling is cross. This this is cross. So the spin texture will follow this way. But for graphene, it's not due to spin-orbit coupling, although it has a form sigma and p dot together. But it produces the kinetic energy. So this will not happen. You will not have another kinetic energy and sum over it. Okay, so usually, yeah, you won't have this kind of combination. So you can delete it. Okay.
Could you induce a Rashba splitting through proximity effect?
Proximity effect.
The 2D picture that has the Rashba splitting.
I think in 2D material you can directly induce it. I mean, in principle, you just make a dual gate device. You apply a vertical electric field, then you have it. Yeah, then you already have it.
So you could have the spin texture that you could spool in graphene.
I think so, in principle. In principle. I mean, you know the Hamiltonian, right? You have a vertical electric field, then you have an electron moving. But for graphene, it's somewhat more complicated. I cannot say for sure, because what matter is really this alpha. How big is it? If it is too small, then it's not very meaningful. And for graphene, the effective mass is 0. Yeah, so I'm not sure. But I'm not aware of it for graphene. But in principle, for any material, any interface, as long as you have a vertical electric field and the electron is moving, you have it. Of course, the key thing here is that this alpha needs to be significant and your electric field need to be big.
But mass is on the bottom here, so shouldn't alpha be very large for graphene?
I don't know, because I'm just not sure about the details, because I'm not aware of it. But I would say it will be there. What matters is how big is it, whether it is detectable. Okay, and okay, any questions? Any questions? So this is one example of spin-orbit coupling with a uniform vertical electric field. Okay, so now let's go to a second example. So this example is more related to us. It's on the second example. Second example, case 2. Okay, here I just say this is case 1 then. Okay, case 1. Okay, here case 2. Case 2 is for centrally symmetric electric field. And this is the case for the atoms. So that means your electric field is pointing in the R direction, So it's in the and you know that in R direction, the electric field will never be constant because of the Gauss law. Okay, because of the Gauss law, it will never be constant. So you always change. So the general form is this. You have 1 over E, a derivative on the potential. Okay, basically you have a potential. This is potential energy. You do the derivative, then you get the force, then you're over the charge, then you get the electric field, right? Okay, so this is basically a negative is the force. Okay, then it's pointing in the R direction. So this is the general form for the centrally symmetric electric field. It depends on the potential. If the potential is weird, then you can have a weird centrally symmetric electric field. But it's always pointing in the R direction. Okay. So you can write it in this way. You just use a R vector over R and dV dr. So this V is determined by the potential inside the atom. You need to include the interaction due to the nucleus and also the screening effect due to other electrons. But no matter how complicated those interactions are, eventually the electric field must be centrally symmetric because the atom has the spherical symmetry. Okay. Then the the spin orbit coupling will be this. Okay, so this is the general form. Then we're going to use S as the spin. Okay, use S as the spin. And then put it in. So this will become 2. And then this will be the S. And then this, let me see, S. Okay, then you're going to plug it in. You're going to plug it in. Just put this inside. If you put this inside, then you have 1 over R dV dr. And then S dot, then you have R cross P. And what is this? This is just the angular momentum operator. So you have this. This is reasonable because in the previous case, the whole system has translational symmetry. Okay, the whole system has translational symmetry. But in this case, the system has spherical symmetry. So that's why it is very normal that you have angular momentum here. Okay. And the S and L commute. I mean, they always commute, right? Because they're in different phase space. They're in different state space. S is on the spinner and L is on the orbital motion. So they commute. So you can see, you can find this relationship. J square minus L square minus S square. I mean, you can easily see, right? S, L plus S, right? So this square then will be L square, S square plus 2S dot L. Then you reverse it, you get this formula. Okay, you get this formula. So here you have this part. You have this part. So you just move this inside. Then you see that the spin orbit coupling will give you the state that depends on the total angular momentum, the orbital angular momentum, and the spin. Okay, and the spin. So we need to pay attention to this part. Okay. So for simultaneous eigenfunctions of J square, L square, S square, the eigenvalues of S dot J is this square L plus 1 minus S. S is 1/2. It's already determined. So you can just write 1/2. So this part is the total angular momentum square. This is the eigenvalue for J square. Okay, this is the eigenvalue of the J square. Of course, with the 1/2, So this one is the eigenvalue of J square. And this one is the eigenvalue of L square. And this one is the eigenvalue of A square. Okay, so if you are not clear, then you just go back to review angular momentum in quantum mechanics. And this equal to L over 2 H bar square for J equal to L plus 1/2. And negative L plus 1 over 2 H bar for J equal to N minus. So because J only have two possible value, you know, summation of angular momentum, right? So J can equal to this or this. So if you if you forget this, just go back to review addition of angular momentum in quantum mechanics textbook. When you have L and S sum together, this J can only take two value, either this one or this one. So you just plug this in, you'll find that this minus thing here will cancel out something. This one will also cancel out something. And eventually, after some algebra, you will get these two results. You get these two results. Okay, so I won't bother to go through the algebra. So you can do it if you want to double check. Okay, so then the first order energy shift for states with quantum numbers N, L, J is this. Okay. Because in an atom, you have this quantum number NLJ. Okay, you have this quantum number. And because this L is here, so you use NLJ. NLJ. Then we just plug this in. Because this will be because this will give you the energy splitting. Okay, this will give you the energy splitting due to spin-orbit coupling. Due to spin-orbit coupling, then you get a result like this: 2m squared c squared. So these are from the spin-orbit coupling term, and then you have a expectation value of this part. You just look at here. Okay, you're going to get this thing. Copy. So this is the Hamiltonian. This is the perturbation. Okay, this is the perturbation term. You have the spin-orbit coupling. So you need to so the energy splitting. You did just the first order of the okay. Then you just put it there. NLJ So this will give you the change of energy. Let me see. And okay, this will give you the energy shift, and this part will only depend on N and L, because this is the orbital part. Okay, this is the orbital part, and then you have h bar square. So you're going to deal with this term. If you deal with this term, then this term will only depend on L and J. Okay, you only depend on L and J. Then you just use this one. So you have h bar over 2 here, h bar over 2 here. Put it out. Pull it out. Then you have two cases, L and negative L plus 1. And this is for J equal to L plus 1/2. This is for J equal to L minus 1/2. Okay, so you put this inside. Then you see the energy shift. Okay, one shift up, the other shift down. Okay, the other shift down. And then let's deal with this term. Let's deal with this term. This term equal to, then you need to do the integration. So the R part of the wave function. NLR squared. Okay, I think probably I'm missing a star here. Okay, I'm missing a star here. Okay, so the size of this splitting depend on this thing. Okay, depend on this. All the others are just constant. Okay, so this is the property of the atom. Okay, so so let's consider for hydrogen, not hydrogen, hydrogenic atom with Z E charges in the nucleus, V equal to, okay, and then dV okay, you do the derivative, you get this. Hydrogenic means it's like a hydrogen atom, but the nucleus has more than one or more than one charges. Okay, so the solution is just the same as in a hydrogen atom, but you just modify it according to the number of charges. So we call this the hydrogenic atom. 1 over R dV dr NL. Then you put this in, you have 1 over R squared, you have 1 over R here. So eventually you have this, and then 1 over R NL, NL. Then you can go back and check. I think people already calculated. Probably you can find it in the textbook or somewhere. Okay, 1 over R squared, expectation value on the hydrogen atom will give you a expression like this. This is 3 L plus 1, 2L plus 1. This is just a 2. This is just a 2. And here here A0 is the bore radius, and alpha, this alpha is the fine structure constant. Alpha is the fine structure constant. Okay, so you plug this in. You have this. You have this. You just put them together. Put it here. Okay, you put it here, then you'll get the result. NLJ. So you plug it in, then you have two. Now this will be Z to the power 4. E square. And then you put this 4 radius here to the power 3. N3 L plus 1 2L plus 1. And then here you actually just multiply L plus 1. So this is the splitting. So basically you use this minus this. Okay. You use this minus this. L minus L plus 1. Then you get the splitting. So here I should not use this symbol. You know what I mean, right? This one means the shift. One shift up, the other shift down. And here I should use what symbol? Delta of delta. Okay. The delta of this delta. Okay. Okay, the splitting. Okay. Okay, you get the idea. Okay. I should say, let me use a better way. Energy gap. Okay, so this will be clear. Energy separation of this. And then eventually you just deal with all this number inside. Then you simplify the stuff. Then you will eventually you'll find a form like this. Okay, so here mc squared equal to 0.5 mega electron volt for electron. And alpha fine structure constant. Okay, so this is the splitting. This is the splitting. Is it okay? Is it okay? By the way, here, if L is 0, then you can already make it 0 from the very beginning. Because if L is 0, then there's no spin-orbit coupling. So what follows? What follow here is for L not equal to 0. Okay, if L is 0, then of course this will not be well defined. But since it's S dot L, if L is 0, then there's 0 spin-orbit coupling. So spin-orbit coupling is not for S state. It's only for P or D or F state. Okay, here I want to emphasize this part. This Z to the power 4 is very significant because it shows that the spin-orbit coupling increases to the power 4 of the charges in the atom. This is a very dramatic dependence. Okay, so let's consider a few cases. Then you understand the magnitude of spin-orbit coupling and why you don't need it for graphene and you need it for MOS2. Okay, so for hydrogen atom, so for hydrogen p electron, let's just talk about this. Okay, so this spin-orbit coupling separation, then you just put it in. Hydrogen, this is 1. Okay, Z is 1, N is 2, so 2, and this is 137 to the power 4, and this is 0.5 times to the 10 to the 6 EV, and L is 1, right? L is 1. So 1, so it will be 1 and 1 plus 1. And eventually what do you get? You get about 44 micro EV. It's approximately 0.15 wave number. So it's negligible. Like if you measure this in CCD, you won't even see it. It's just very, very small. You probably cannot even resolve it. It's very small. So for hydrogen atom, spin-orbit coupling is negligible. Okay, so let's go to graphene. For carbon atom, the p electron. Okay, so we know that in graphene is sp2 sp2 hybridization, right? So you are dealing with the p electron. Okay, so there is spin-orbit coupling because you're dealing with p electron. So let's so here Z is 6. Z is 6 for graphene. N is 2. L is 1. Then this will be 6. This will be 6. Okay, 6 to the power 4. And then here is 2. Everything is straightforward. The same. And then you still have 1 plus 1. So eventually you get 57 milli EV. It's about yeah, just use milli EV then. Okay, so but here you see this is already sizable. Like you're supposed to see like a spin-off coupling 57 milli EV. But however, here you have to say the screening is not included. So screening is what is affecting this thing. What is affecting this thing? This is when you don't have any screening. That means you have one electron seeing a nucleus with 6 charges and no other electrons around. Then the spin-orbit coupling will be 57 milli EV. But in reality, you have 1 electron and 5 other electrons around. Those electrons will screen out the nucleus. So what you will see here will not be this Coulomb law. It will be a Coulomb law suppressed. That suppression is actually significant. Okay. So, but anyway, let's neglect the screening for now. I want to show you this increase of the spin-orbit coupling with the charges. Okay. So for MO atom, like in MOS2, for MOS2, the electrons that we're interested is the 4D electron. The 4D electron. 4D electron. So here N is 4. D means the Z. Let me see. So for MO, so if you go to the periodic table, MO has a configuration of Kr and then 4D5, 5s1. So the outermost electron are the D electron. 5 electrons are in the D orbit, and 1 electron is in the S orbit. Okay, so N is 4. Let me see. So the Z, the Z is 42. There are 42 charges in the nucleus. 42 charges. And N is 4. And then L. What is L? L is 2. L is 2. It's a D orbit. So then you just do the calculation. Then you have 42 to the power 4. This is a huge factor. And then 4. You just follow this formula. Plug this in. Then you have 1 over 37 to the power 4. And then 0.5 times 10 to the 6 EV. 6 EV. And then 2. So this will be 2 and 2 plus 1. And then you get a spin-orbit coupling of 5.8 EV. EV. So you can see for graphene is 57 milli EV. And this is 5.8. So you can, if you change it into milli EV, it will be this, like about 100 times of in carbon. Yeah, in carbon. Yeah, graphene is this, and this is this. Okay, so let's take care of the screening effect. After included. So for graphene, the spin-orbit coupling go to about 1 milli EV. And then for MOS2, the spin-orbit coupling go to about 140 milli EV. So this is reduced for an order of magnitude. Okay. But you see the ratio is about 100 times. Okay, it's about 100 times. So here you compare this to this, is about 100 times. And after you increase the screening, is also about 100 times for MOS2. Okay, so that's why in graphene, spin-orbit coupling is negligible, but for MOS2 is significant. Okay, the key thing is this factor. This factor. This is a very important factor. So when it is heavy, it goes to the power 4. Okay, so go to the power 4. Okay, finally, let's make a comparison of the spin-orbit coupling to the energy level of the hydrogen atom. So the energy, just compare with the level, the energy of the level. So En equal to negative m. This is the formula that you can find, I think, in the textbook. Okay, so you can change the form in this way. Okay, so you change this form, and then this one you can group it into this is the fine structure constant. So alpha is the fine structure constant. Okay, so what is the level here? So you compare. Let me see. So the separation is this. Copy. Compare to the splitting due to spin-orbit coupling. So you can already see it here. This, and you can mix them together. I mean, you can already see this is alpha squared. This is alpha to the power 4. And this is approximately 100, basically 100 times. So you can see it is about 10,000 times smaller. 10,000 times smaller. But of course, you need to consider this factor as well. Okay. The other factors. Okay, so you plug it in. You will Z. So then this is called the Balmer energy. Balmer series is the lines for the hydrogen atom. Okay. Okay, so spin-orbit coupling. So just give a summary. Spin-orbit coupling is a relatively weak effect. Okay, so you can from this relationship you can see it is about 10,000 times weaker than the Balmer energy. But the Balmer energy is big, like in the order of EV. Okay, or 10 EV. So even if it is 10,000 times smaller, you're still in the measurable range if you have a sensitive equipment. Okay, and also, I mean, for hydrogen, of course, it's small, but once you have this factor here, this thing here, the charge will just make it like if you have 40 charges, then square, then you have a big enhancement. So for heavy element, the spin-orbit coupling is also sizable, not as strong as the general energy level, but if you consider spin-orbit coupling in the context of a spectroscopy, is quite measurable. And actually, for condensed matter, that is an important part of the band structure. For MOS2 is very important. Okay. So any questions? So in today's lecture, I gave 2 examples. I mean, I thought I will go through them not very slowly, but somehow it's still use quite some time. Okay, I hope you can follow comfortably and you can understand. I mean, these are some like a basic of spin orbit coupling. Any questions? Is it clear? Okay. Sun Yang, you have any questions?
I'm okay.
Okay.
It's clear. Yeah.
Okay, good. Okay, if no more questions, then we'll end the lecture here.